Here we're given temperature and pressure, and we start with a mole of methane and a mole of water, and then we let the system go to equilibrium. Which equilibrium we reach depends on which molecules we consider to be involved in reactions. Here we're going to assume carbon dioxide, and hydrogen can form. And we want to use the temperature-dependent heat capacities to calculate heats of reaction and then calculate Gibbs free energy of, in this case, formation of each of these species as a function of temperature. So there's two ways you can solve this type problem. One, you can write down two reactions. So let me just write them down. And if you were to use this approach, we would have an extent of reaction for each reaction. We set an equilibrium constant equal to fugacity ratios, or for ideal gases, which is what we're assuming here, partial pressures. And when we have more than one reaction, it gets messier, if you like, more difficult. The other approach is to minimize the Gibbs free energy and not specify which reactions occur, but just specify which species can form. Now, this approach was demonstrated in another screencast for just the second reaction here, the water-gas shift reaction. And what I want to do here is show how we do this when we have more than one reaction. By the fact we compare it to water-gas shift, we have one more species, namely methane, that can form. And what we're going to do is minimize the Gibbs free energy, the total Gibbs free energy, so number of moles times Gibbs free energy per mole for this mixture, which is the sum of the moles of each species times their partial molar Gibbs free energy. And that is equal to the standard state Gibbs free energy of formation of each species, and then RT log of the mole fraction times the pressure. And we can write it this way because we're assuming ideal gases, and fugaces just become partial pressures. So this is what we want to minimize. We have to account for the fact that the number of carbon atoms, the moles of carbon, if you like, moles of oxygen, hydrogen doesn't change. So we're going to have a constraint. We're going to use spreadsheet and solver to do the minimization, with the constraint that the number of carbon atoms coming into our reactor is the number of carbon atoms coming out, and likewise the same for the other two atoms. So when we use solver, we'll use the constraint option to select these. We also will check the box that says make unconstrained variables non-negative. So in the solver, there's a box, and we're doing that because we want the number of moles of these species. That's what we're going to be solving for. Or in other words, we're going to say, how do we vary the number of moles at equilibrium in order to minimize this Gibbs free energy? Well, let me show you the result when we run that minimization in spreadsheet, then I'll briefly show the spreadsheet. So here are the equilibrium solutions. We calculate the number of moles at equilibrium. Remember, we started with 1 mole methane, 1 mole of water. So this column is the number of moles at equilibrium. This is the mole fraction. The total number of moles is almost 3 for these particular conditions. And then what I've done just as a check on the spreadsheet, I compared to an online calculator, and the reference to this is given in the spreadsheet, to see if we're getting pretty similar values. Indeed, they differ most about 3% or so. And that difference is exactly which heat capacity term we use to try and represent the heat capacity over this temperature range. It's going to give us slightly different answers. And so this confirms that indeed spreadsheet's doing what we think it's doing. Let's look at the spreadsheet briefly. So here's a copy of part of the spreadsheet. This column we enter our starting number of moles. These are the values that we adjust with solver in order to minimize the Gibbs free energy. Notice we're minimizing Ng divided by RT. That's pretty arbitrary, but we decided that's convenient, making it dimensionless. And we calculate, as I showed, each of the partial molar Gibbs free energy that add up to give us that total Gibbs free energy. Where over here are the constraints. Number of moles of carbon coming in, hydrogen, oxygen, and then indeed we set that difference, which is here, as constraints in solver. Indeed, we get very close to 0 using solver. The rest of the spreadsheet has the heat capacity data, the heats of formation, therefore calculates these Gibbs free energy of formation at the temperature 950 Kelvin. So the big advantage of using this Gibbs free energy minimization is that we can do the calculation. If we have 5 reactions, we add 2 more species. The calculation doesn't become more complicated. We just have another value or 2 that we add to the Gibbs free energy, and if we have other elements, we add those also. And we use the exact same approach, whereas we get more reactions solving those equilibrium expressions. With multiple extensive reaction gets much more complicated.